Today I'm going to talk about hydrogen storage and transport. Hydrogen is seen as a key player in the future of energy, but its implementation is hindered by challenges in transportation and storage. While the potential of green hydrogen is enormous, scaling up these technologies requires overcoming significant barriers, especially in infrastructure. Why do we need hydrogen transport and storage? Currently, 99% of hydrogen is produced from fossil fuels, generating approximately 830 million tons of carbon dioxide annually. This is equivalent to the emissions from 600 million cars. One challenge to change this is to develop efficient storage and transport solutions for green hydrogen so that the decentrally produced clean hydrogen can be delivered to the end user at low cost. How can hydrogen be stored and transported? Hydrogen can be stored and transported using physical or chemical methods, each of which has its own specific advantages and disadvantages, which we will discuss in more details in the lecture. Depending on the scope and application, different methods are used. When selecting the appropriate storage technology, the factors of energy density, costs and feasibility must be taken into account. How to compare different storage technologies? There is no perfect storage solution. Each method has its pros and cons. Key evaluation criteria include storage density, energy requirements, cost, lifespan, operating parameters, and material handling. These factors are essential to assessing each storage method. For example, while liquid hydrogen offers high energy density, it requires extreme low temperatures, making it less practical in certain settings. Understanding the specifics of each criterion will help determine the right choice for a particular application. There are three main physical methods: compressed hydrogen, liquid hydrogen, and pipelines. These methods have different advantages and disadvantages, which are summarized in a table on this slide. Compressed hydrogen, for example, is easier but less efficient over long distances due to the volume it occupies, while liquid hydrogen has a high energy density but is expensive to maintain at low temperatures. Pipelines can be efficient, but building the infrastructure is costly. Let's speak about liquid organic hydrogen carriers. This is the first chemical storage method we'll discuss. LOHCs store hydrogen via hydrogenation and release it through dehydrogenation. LOHCs offer an energy density of 1.86 MWh per cubic meter, comparable to compressed and liquid hydrogen, with the added advantage of being a liquid, making it easier to transport. However, it requires a complex process for hydrogen release. Despite these challenges, LOHC technology is promising due to its flexibility in transport and storage in conventional fuel tanks. Metal hydrides have a high energy density of up to 3.65 MWh per cubic meter. Hydrogen is stored via hydration directly in metals and is released as high purity hydrogen through dehydration, requiring no additional purification. However, metal hydrides are expensive, toxic, and heavy. The main advantage lies in their long storage life and stability, making them ideal for stationary application. Although their cost and weight limit broader adoption. Ammonia is often mentioned as a potential hydrogen carrier. It has an energy density of about 3.5 MWh per cubic meter and can be liquefied at 10 bar, unlike liquid hydrogen, which needs to be stored at -253 degrees centigrade. Ammonia is already widely used in industries such as agriculture. However, separating hydrogen from nitrogen in ammonia is costly and requires large facilities. Despite this, ammonia's ability to be stored and transported as a liquid makes it a strong candidate for future hydrogen infrastructure, especially where existing ammonia supply chains can be repurposed. Iron can store hydrogen through a steam iron process. where iron oxide is reduced and hydrogen is released through steam. It offers the highest theoretical energy density of 3.9 MWh per cubic meter and is a low-cost option without expensive materials. However, high temperatures of around 500 degrees Celsius are required for the process. Unlike ammonia, iron doesn't need purification, making it simpler to handle. This method is still in its early stages, but shows significant promise for large-scale, low-cost hydrogen storage solutions in the future. How to decide which transportation technology to use? The choice depends on four main factors. First, quantities. Large quantities favor liquid hydrogen, ammonia or iron. Second, distance. Long distances are best suited for liquid hydrogen, ammonia or iron, while short distances work with compressed hydrogen or LOHC. Third, cost. Iron is inexpensive while metal hydrides are costly but efficient. Fourth, safety. Iron is non-toxic and safe to handle, while ammonia is toxic and compressed hydrogen poses high pressure risks. In conclusion, each technology offers unique advantages and drawbacks, and the decision should be based on the specific needs of the application, considering the balance between cost, safety, and practicality.